Okay, so we have here the equations we're going to need to derive the ground state energy for a hydrogen atom, just like Niels Bohr did. These five equations here are what we'll need. The first one says that the angular momentum of the electron around the nucleus is quantized. It only comes in integral numbers of h bar, which is h over 2 pi. The second equation here tells us that the centripetal force that keeps the electron in orbit is provided by Coulomb's force, and that the total energy is the sum of the kinetic and the potential energy, with the kinetic energy being 1/2 mv squared and the potential energy being kq squared over r. And that's actually negative in a bound state. Okay, so before we get started, we're going to rearrange a couple of these equations and then we'll take them over to the next panel and start using them. I'm going to want to, first of all, rearrange the first equation and solve it for V. So this is going to yield for me that V is equal to NH over 2 pi mr. Okay, so I'll need that. And then I want to also recognize in this equation here that I can cancel out an r, and I would get that mv squared is equal to kq squared over r. Okay, so I'm going to use these two equations. First of all, we're going to solve for r, and we're going to find the Bohr radius. That tells us where this electron is in terms of a distance from the center of the nucleus. And this is a classical idea, but we are using some quantum mechanics from equation number 1. Once I find that radius, I can use that radius to go back and use my total energy equation to find the ground state energy. And so I bring this equation over, and I want to solve this for r. And I'll go ahead and do that now. And so we're going to get that r is equal to kq squared over mv squared. And then I'll use this expression that I got for v, and I'll plug that into v squared here. I'll do that on the next screen here. So when I do that, I get that r is equal to, I'll rewrite that, kq squared over mv squared. And that's going to be equal to kq squared over m, and v squared, well, v, remember, was nh2 pi over mr. So that's going to be, the m is still there, so the m is there. The v squared is going to give me n squared h squared over 4 pi squared m squared r squared. Okay, and I can bring this up and reduce this. So the bottom of the bottom goes back up to the top, and I'm going to get k, I got my kq squared, and then also up top comes the 4 pi squared m squared r squared, and then this is now over m n squared h squared. This m cancels with one of these m's. And notice now that I've got an r squared over here and an r over here. So I'll cancel out an r on both sides, and then I'll get that 1 is equal to kq squared 4 pi, that's a pi squared, I forgot, pi squared r over n squared h squared, so that r is equal to the reciprocal here, n squared h squared over 4 pi squared k q squared, and then I still got this 1m right here that I forgot. Now, when n is equal to 1, then what we have is the Bohr radius. So I'll write that as r sub capital B, and that gives me h squared over 4 pi squared k q squared m. So I'll need the Bohr radius to solve for the energy. So now we've got the Bohr radius. Let's have a look at the energy equation. So for the energy, I'm going to use my total energy expression. And that total energy expression, remember, was the kinetic energy. So the total energy is equal to the kinetic energy, 1/2 mv squared. And then it was minus kq squared over r. Now you could go and substitute that expression for v that we had into this equation right here. And you could find a common denominator, and then you would get an expression involving Bohr's radius. You could simplify that and then plug in Bohr's radius one more time, and you could get to the answer that way. It's a bit longer, though, and I had forgotten the first time I did this, or the second time I did this, that there's a shortcut. I remember that's shorter than that. We can realize here from, if we remember the force equation, we had that m v squared over r was equal to the centripetal force was caused by the Coulomb force, kq squared over r squared. We already used this once before, but we can use it again. So what this tells me, if canceling an r on both sides, I get that mv squared is equal to kq squared over r. But I have mv squared right here. So the mv squared is kq squared over r. So I get 1/2 kq squared over r minus kq squared over r, and that's going to give me negative 1/2 kq squared over r. And that makes it a lot easier than what I was suggesting before, because now I just plug in the Bohr radius for which I've already solved, and I should get my answer. So doing that, I'm going to get 1/2, I got my k, q squared, and then the Bohr radius, plugging that in, is going to be over, this whole thing is over, that was n squared, h squared, over 4 pi squared. I'm going to leave my n in here. I put my n back for the Bohr radius because I want to try to get an expression for various energy levels. It was kq squared, and then m. So flipping the bottom of the bottom back up on the top, I'm going to get 1/2 k squared. I got a k here and a k here. I got a q to the 4th. Don't forget my q to the 4th. I got my 4 pi, and then I've got my m. And this is all going to be over n squared h squared. N squared h squared. So let's bring this over to the final. Let's bring this over to a final pane and clean it up and see what we get. This is pi squared. This pi squared. Make sure I got everything right. Okay. Got 2 k's. I got 4 q's. I got a 4, but I got a 1/2 of a 4. And then that looks good. So let's clean this up. So what that's going to give me, I had 1/2 of 4 pi squared, so that's 2. And this is going to be the total energy now. The total energy is now equal to 2 pi squared, k squared, q to the 4th. I had an m, and then I had an n squared and an h squared. And so for n equal 1, again, this is for all the different energy levels, I can get the ground state energy when n equals 1. And that's going to tell me that, and this whole thing is negative, by the way, remember? And so that's going to tell me that the ground state energy when n is equal to 1 is equal to negative 2 pi squared, k squared, q to the 4th, m, and that's, of course, of the electron. Q is the charge on the electron, and then h squared. And then this, I'll leave for you to confirm, is going to be in joules, but it should work out to about negative 13.6 electron volts. This is what Bohr did, and now you can do it too. Later, Dirac came and added some relativistic mechanics in order to get a more precise result. And then later, Feynman and others added other quantum mechanics to it with some probability and some different probabilities added in. We're getting ever more and more precise results. But it's quite remarkable how well Bohr was able to calculate the radius of a hydrogen atom as well as the ground state energy, just using a little bit of quantum mechanics and a medium amount of classical mechanics.